Hello and welcome to today's presentation. My name is Pete Sanders. I'm the VP of Field Application Engineering here at Napatech. And today I'm going to talk about the importance of true zero packet loss in cybersecurity use cases. So let's get started. So first I'll just start explaining what packet capture is for those that don't understand. So all cybersecurity network monitoring devices use packet capture in one form or another. Packet capture devices are passive to the network, okay? They're not visible to the network. They're not an endpoint. They're just passively sniffing packets from the network. And typically, the requirement is 100% capture of all packets at all line speeds, regardless of network load and packet sizes. Here's how they're typically deployed. One is with a tap, which can be a passive or active tap. And basically what the tap does is it goes between the switch and router in this instance, and a copy of every packet is sent to the packet capture device in both directions. And a switch can also mirror traffic to a span port, and that span port can then deliver the packets to the packet capture device. Packet brokers have similar functionality in that regard, where ports can be load balanced and to any kind of monitoring devices you might have. So that's what packet capture is. So what are the challenges to packet capture? So the challenges are, especially when trying to use a standard server NIC. Maybe it's a NIC built into the server. Maybe it's a NIC card from a variety of vendors that are out there. They're really designed for client-server communication, low latency, packet-by-packet delivery. Packet delivery is not guaranteed at high network loads. They're not optimized for full throughput at any network traffic load. So when a NIC, a standard NIC, is used as a capture device, packet loss can occur. The other challenge is that NICs with multiple interfaces, they're trying to monitor traffic on the network. Packet ordering is not guaranteed across interfaces. So, the reason why packet loss isn't a problem is that you have higher level protocols that activate retransmission. So packets are dropped, those packets are retransmitted again. But in the case of packet capture, because the device is passive to the network, it's not part of the network, it's not visible on the network, it can't use those retransmission protocols. It just needs to be able to capture everything, okay? And so the NIC is out of band. You can see this is a packet capture use case here where it's out of band monitoring, okay? So using an off-the-shelf server NIC designed for communication will most likely drop packets at high network loads. Here's some of the effects. Here's some examples of negative effects of packet loss in network recording. And so network recording is a device that records all traffic for a period of time, and then typically they start overwriting the oldest packets. So network recording gives cybersecurity and network engineers the ability to go back in time and retrieve packets from an event on the network. Okay, they can use that packet data to analyze past cybersecurity issues or network performance events. Whatever they need that packet data for, it's there. Okay, so this packet data can be then, of course, archived for historical purposes, whatever. But that's the use case and the value of network recording. Now when packets are dropped by the recording device, okay, you don't get a complete result of your analysis. So essentially you end up with an incomplete picture of how, when, and why a particular event on the network transpired. And so it becomes extremely difficult to root cause an event when you don't have all the data. It's as simple as that. Okay? And this is, a basic picture of what network recording is. Again, it's out of band. There's typically a server and a lot of storage, and those packets are written to disk, and then there's usually an indexing mechanism that allow you to search those stored packets. So here's another use case. So intrusion detection system, an IDS. Okay, packet loss in an IDS has a big impact on cybersecurity events that IDS would generate. So an IDS typically looks at packet data on a flow-by-flow basis, and based on a set of rules, if that flow meets the criteria, an event is generated. But what happens is, with as little as 3% packet loss, you can have upwards of 10% missed alerts coming out of your IDS into your scene. This data is from a Suricata conference back in 2019. These are some of the open source solutions that we support. Now you can see when you get up to 25% packet loss, you're missing half of your alerts. So not a good situation. Now here's another example. So typical IDS systems have the ability to do IDS file extraction, right? So you want to extract a file sent over a flow, but you need all the packets to extract that file. So you can see it's even worse for file extraction, right? 4% packet loss, 10% failed file extraction, 5.5% packet loss, you're at 50%. You can't extract that file that was sent via that flow. So you can see there's a big impact on packet loss. Very little packet loss is required to have a big effect, a big negative effect on your cybersecurity strategy. So what I'm going to talk about now is the technology that Napatech uses on their Smartnics to achieve zero packet loss and all the other features and capabilities that we provide. So it's in a device called a field programmable gate array, which is a logic device, okay, and it has a large array that can be programmed to do different things. And basically, you can think of it as a programmable ASIC, okay, a chip. And the value is that you get the performance of hardware with the flexibility of software, meaning you can update the firmware in the FPGA and change the functionality, fix a bug, add a feature. And so it can be reprogrammed in the field by the end user. And so no hardware, the physical hardware doesn't need to change. Once that initial investment in the hardware is made, then the platform can be updated, unlimited number of times to support other use cases. This is the technology that's built into Napatech Smartnics. So let's just talk about, again, how a Smartnic addresses these challenges. The Smartnic hardware and the firmware and the FPGA are purposely designed for packet capture, okay? So the architecture is optimized to capture 100% of the network packets regardless of the utilization or packet size. Packets are time-stamped in hardware, and this provides value to other use cases where you're doing latency measurements or you're doing jitter analysis. Physical ports, so multiple ports on the Smartnic, can be merged into a stream, so the exact order that they traverse the network is maintained. Large onboard packet buffers. So on the Smartnic itself, there are large packet buffers, and the value there is that when there are events on the network with extremely high utilization, we call those microbursts. So microsecond bursts of traffic at 100% utilization, this is where the packet loss can happen. And so the buffering on the card helps eliminate that, but it also eliminates any potential system bottleneck where maybe the PCI bus is busy for a few milliseconds or microseconds. That's what the buffer on the card does. But then we also have the ability to create very large host buffers, and that's for the application that is trying to keep up with that network load. It's a big buffer, it's a big FIFO. And some of the other features that are valuable is we bypass the kernel using a method called kernel bypass, and we DMA directly in hardware to those host buffers that your cybersecurity application is pulling packets from. And we distribute to many host buffers, up to 128 based on flow. And this is where large scale multi-threaded applications like Suricata can process extremely large amounts of traffic without packet loss. Deduplication discards duplicate packets, or it can count them, or both. So if there are duplicates on the network, you don't need to analyze that flow twice. Let's preserve those CPU resources on the server for the cybersecurity application. And then we also have stateful flow processing, so which means that the application receives the first packet or two of a flow and then can make a decision and say, I don't want to see any more of that flow because it's not interesting to me for whatever reason. Maybe it's a video, maybe it's an elephant flow, large file transfer. No sense in looking at that anymore. So then basically then the hardware, the Smartnic, then will drop that flow until it terminates. And then for inline cases, which we haven't talked about too much, but where the Smartnic is inline with the network, not out of band, this stateful flow processing can forward known good flows or block flows from entering or leaving the network. And it's all done in the NIC itself. So this is our capture software that runs on our Smartnic, and we guarantee full throughput, receive and transmit for any packet size, 0 packet loss, 500 millisecond buffer on the card, and we've spent significant time optimizing PCI bandwidth so that you get full performance over the PCI bus. And then we guarantee the packet ordering. So the application always is getting the packets in the correct order that they traverse the network. The other focus is low CPU utilization. So use very little of the CPU so that your cybersecurity heavy lifting application has all the cycles it needs to process the incoming packet data. And we've optimized our architecture and products around both Intel and AMD CPUs, and some of the things that we do is we optimize the cache performance in our host buffer system, and which basically allows higher CPU core utilization, which means that because we do this advanced load distribution, we spread the incoming flows very efficiently across all the CPU cores, so you can maximize your CPU cores and not have any packet loss. And here's just a high-level overview of what I've discussed: zero packet loss, burst buffering on the card, time stamping, packet sequencing. Okay, we guarantee the order of the packets. Our PCI performance has been optimized along with the cache. We do our what we call multi-CPU distribution, or receive side scaling is the industry standard term, but this allows us to spread that incoming traffic based on flow, across many CPU cores, up to 128. In our per flow processing, deduplication, we also have the ability to do traffic replay and traffic generation for test and measurement applications or just test applications. And lastly, we have the ability to retransmit packets, port forward packets coming in on one port, out another port, doing some filtering along the way. So I'm sure many of you can see that this feature set is very similar to what you would find in a packet broker. And here's a high-level view of the architecture, just so you can pictorially see what we do. But essentially, we have 2 ports, 2 MACs. We merge those channels. We apply a timestamp. Okay, and this is all done in the FPGA hardware. We do any packet decoding. We gather statistics. We do flow recognition and processing. Any filtering or slicing of the packet data, compare, buffer split, meaning RSS to multiple CPUs, and then to our buffer system, and over PCI Express to the host buffer. So that's just a quick high-level overview of what we do in the hardware to provide a zero packet loss solution. So, here are some of the use cases that you can use the Napatech Capture Smartnic. Cybersecurity, which we've already discussed. Network recording and replay, which we've discussed as well. Other things like subscriber analytics and monitoring, test and measurement, network and application performance monitoring, and then open source or homegrown commercial apps that can do a variety of different things. Any use case where you want to see everything on the network and you want it delivered extremely efficiently to your application. These are some of the open source projects we work with: Suricata, Snort, Zeek, T-Rex is a traffic generator, and then we support open APIs like DPDK and also libpcap. So if you have a libpcap based application, you can use Napatech technology right away. And so here's the families of software we make available for our Smartnic hardware platforms. Capture we've already discussed. Capture with flow processing we've discussed, but again, gives you the ability to have an action on a per flow basis. Inline is similar to Capture, but it's a bump on the wire use case. So it's lower latency because it's inline, but again, it gives you the ability to block, forward, essentially perform an action on a per flow basis at speeds of up to 100 gigabits per second. And then virtualization, we have a virtualization solution which accelerates OVS and OpenStack for SDN, NFV environments. Any virtual environment, we basically accelerate the performance of OVS in our Smartnic. So I'm going to briefly go through the hardware here. So just this is what our Smartnic looks like. In this case, it has 200 gigabit interfaces, but these can actually run at different speeds. They can run at They can run it 4 by 10 on each port, 4 by 25, 2 by 40 gigabit, 2 by 100 gigabit. We have time stamping and time synchronization capabilities, and it's a very rugged platform with state-of-the-art monitoring and buffering on the card. So that's a high-level look at it. Here's an example of one. This is our NT200. It's a full height, half-length form factor. It utilizes a Vertex UltraScale Plus VU5P FPGA. It's got 12 gigabytes of RAM on it for buffering or a flow table. It's a 16-lane PCI Express Gen 3. And you can see with this 2 by QSFP28 network ports, you can do a lot of different things with it. 40, 100 gig, breakout cables to 4 by 10 and 4 by 25. We have time synchronization capabilities. It's less than 75 watts. And we have two versions, one with what we call self-contained cooling, which means it basically regulates and controls its own cooling. And then this is the passive heatsink version. And the NT100 is very similar, same FPGA. This one has individual ports that can run at 1, 10, or 25 gigabits. It has 8 gigabytes of RAM. But again, very similar to the NT200, same form factor. And lastly is the NT50, which is targeted for low profile use cases where there's less space in the server. It uses a Kintex KU15P FPGA from Xilinx, and it's got 10 gigabytes of RAM, and it's lower power and lower cost. So just a quick corporate overview on Napatech. Over 18 years of experience developing FPGA-based SmartNICs and delivering them to our OEMs mainly. You can see the list of our top global customers down here, but we also have many OEMs that embed our technology in their network appliances. So you may buy a cybersecurity solution from a third party, and most likely it has an Napatech SmartNIC built into it. But we're a solid company. We've been in business for, like I said, 18 years, and we're also a public company, and we're listed on the Oslo Stock Exchange. So I hope you enjoyed this presentation. My contact information will be available, and feel free to reach out if you have any questions. I'd be happy to answer them. So have a great day, and thank you for watching.